Hello everyone, and welcome back to K-Math, creating educational videos that change the world. Today, we will be proving the squeeze theorem. The squeeze theorem. So many of you have probably heard of the squeeze theorem from your calculus classes. If you don't remember, I'll basically reiterate it. So basically, at least the one I'll be proving, which I think can be pretty easily generalized to functions, is if you have a sequence x sub n, and this sequence approaches some limit L, and another sequence x z of n, and for z of n, it also approaches L, and you have the condition that x of n is less than or equal to y of n, is less than or equal to z or n for all n in the naturals, then this implies that y of n, the sequence, also approaches L. So that is what we're going to be trying and prove today. Okay? And if you've seen this in calculus, I think it's basically like if f of x, like limit as x approaches like infinity, f of x approaches some limit, and like when I write this, I basically mean limit as n approaches infinity of the sequence x of n approaches L, but it's just shorthand. Or sometimes I'll write lim x of n. That also just means the limit as it approaches infinity. So if this is true, and then limit of, I don't know, let's say h of x also approaches L, and f of x is always less than or equal to g of x and h of x, then g of x also approaches L, right? The limit as it approaches some value. But yeah, so this is kind of, I feel like, an intermediate step in proving it, but I'll only be proving that this is true. Okay, now let's recall what it means for something to approach a limit. Okay, for x of n approaches L, that means that, so the first step in our proof is that we set our epsilon to be greater than 0. Okay, so let epsilon, we should let epsilon be greater than 0. And remember, epsilon is any arbitrary number that is greater than 0. And so if x of n approaches some limit L, this means that the absolute value of x of n minus L is less than epsilon for there exists, this means that there exists a n in the naturals such that for all n greater than capital N, there exists capital N1, let's call this N1, then this is true. Alright? And so, basically, what we have this fact, and since we also know that z of n approaches L, there exists n2 in the naturals such that for all n greater than n2, it's true that z of n minus L is less than epsilon. Okay? And so, this is the same thing as that. See, like epsilon is the same thing as that. Okay? And so, how should we go about this proof, right? Because what we have to show, I should have done this first, is that for all, there exists n in the naturals such that for all n greater than or equal to n, we have y of n minus L is less than epsilon, right? And so, how should we do this? And we also have the fact that x of n always less than y of n, always less than or equal to z of n. So, let's decompose this inequality, and by that I mean we can expand it, right? If we this is the same thing as saying x sub n minus L is less than epsilon is less than negative epsilon, right? That's just by absolute value. If we add L to both sides, we just get L minus epsilon is less than x of n is less than L plus epsilon. And this is like the epsilon neighborhood definition of our limit, right? If you've seen it before. Similarly for z, we can write this. right? Now, let's use this inequality, right? You see, this x of n, well, what's also less than x of n? L minus epsilon, okay? Z of n, what's greater than L plus epsilon? So if we combine these three, what we will get is that L minus epsilon is less than x of n is less than or equal to y of n. Not y of n. I keep saying of. When I say that, I just mean sub. Z of n is less than L plus epsilon, right? And so we get that y of n is greater than L minus epsilon is less than L plus epsilon. And remember, this is for all n greater than or equal to n sub 2 and all n greater than or equal to n sub 1. This is true, right? Because this is only true for this, and this is only true for this. So when we combine them, this is only true if this is true and this is true. So if we turn this back into absolute value, we just get y sub n minus L is less than epsilon. And remember, this is only true if this up here is true and this up here is true. So basically, this is true for all n1, n2 in for all n greater than n1 and also like it has to be greater or equal to n2. Or we can write that n equals the maximum of n1 and n2 and simply compress that to say this is true for all n greater than n, right? And so basically through this we've shown that there exists an n such that this is true, right? And this n is basically just picked by picking the maximum of n1, n2 from these two. And so we've proved our squeeze theorem. It's that simple. Thank you guys for watching this K-Math video. This is the first video in a series of videos on proving things. It's called Real Analysis. I hope you guys enjoyed. Make sure to like and subscribe. Leave a comment on which topic you would like to see next. Physics, math, whatever. And I will see you guys next time. Goodbye.